What's going on, my Weld family, and welcome back. Today's lesson, we're doing open root pipe tutorial on aluminum on a 6G position. We got Travis here, Travis Field. He's gonna show us the introduction to aluminum, and we're using 6061 aluminum pipe and 4043 filler wire for aluminum. So Travis, welcome back again.
Thank you.
It was just pretty much yesterday that we saw you, so I don't know why I was saying welcome back. Anyways.
I've been here the whole week.
He's been here the whole week.
We were golfing, we were doing everything. Going for dinners.
Again, I'm Mark Gilo, I'm the welding supervisor. This is Abraham Quintanilla. He is a lead instructor, and Travis Field again. Aluminum pipe. Tell us, Travis, what do we got here on the board, and what do we need to know?
Well, essentially this is just ideas of aluminum. Basically, aluminum is a very difficult metal. It forms oxide very rapidly, but it's a very difficult metal to weld, and there's a lot of variables that the person has to follow and remember while welding this. But we'll start off basically aluminum has an oxide layer that melts about 3700 degrees Fahrenheit, and when you brush this oxide off, the material underneath the oxide melts at 1220. Now, basically when it comes to brushing, you brush all these in one direction, whether it's downward stroke or upward stroke. And I know at the training facility that I spent a lot of time at, Jerry College of Welding, Jerry actually has an arrow, upward arrow, that you brush always in one direction. The reason being for this is because you remove the oxide with one stroke in one direction, but if you go backwards, it digs into the soft aluminum, and it embeds the oxide into it a lot deeper. Okay. But basically when it comes to aluminum, there's two different fit-ups that I've been taught. I've been shown at the trade facility there. There's extended land fit-up, and there's a open root butt joint here. And with the extended land fit up, essentially the way it is you have a 332 land and 332 extended land. They'll be butt up tight, and you don't have to use a backing purge unless for critical applications, but you can slam it up tight. Usually if you wear a shade 11 lens, it helps with removing the gloss and glare of the weld puddle. But if you use a shade 11 lens, you can give a surge of current. It'll remove a lot of the cleaning action. You'll see the weld puddle. It'll melt the seam in the middle of the weld puddle, and it'll form a weld puddle. And then you'll see it go slightly concave. When it goes concave, you can just dab into the weld puddle there, and then you'll see it kind of grow. And then you move to a leading edge, and then repeat the process all over again. Okay,
so for this extended land, it's critical for it to be a 332 land. Anything more than that, it's going to be some hard penetration. It's going to be hard to get the penetration inside the root. If anything bigger than a 332.
That's true.
Okay.
Yeah.
You get away with a 116?
Oh, you can. Smaller size pipe.
Okay. Small diameter pipe.
Yeah.
All right. Go ahead, Trev.
Also, the butt weld, we'll have a normal, typical butt weld. I'll be using a 1/8 gap in the video and a 1/8 filler metal, and I'll have the filler metal on the outside of the pipe. So I'll be dabbing in the outside of the pipe there, and the root pass will be going in via capillary action, but that will be purged, that particular pipe. Also in the video, I'll be using a 2% lanthanated with a sharp point, so the arc is a lot more focused when I do the root pass. When I switch to the, pardon?
Can you backfeed it?
Oh no, aluminum in general is very difficult to weld, but I have found in practice while trying different welding techniques, I found that when trying to backfeed the arc, the electricity seems to know where the filler metal is, and even if I'm on the leading edge, the arc will heat up the filler metal, and they'll start. It's like an arc. The filler metal arcs out to various parts on the material.
You know, I understand that. Yeah, sure. So, now, yeah, we're at the tungsten part, so it has to be sharp at first, so we can make that. Once you start creating that arc, it's going to make that dull, that perfect dullness where it needs to run that open root.
Well, it depends on like a lot of applications, aerospace, automotive, NASCAR. It very depends on the tungsten prep and also the kind of tungsten. I believe there's a manifold manufacturer on YouTube that has videos where he's tried different tungstens, and he's had different etching, okay. And he's had different weld results with different tungsten and how they hold up at elevated temperatures. I've also found that 2% thoriated seems to crack in the middle when you have it at elevated temperatures.
Yeah. Another thing, Travis, so when we run the root pass, you recommend 2% lanthanated, correct?
Well, it doesn't necessarily matter which tungsten is used, but it's only a personal preference.
Okay.
Yeah, and the reason I'm using a 2% thoriated or is because it's not balling up as readily and as freely as a pure. And so because it's a sharp point, I'm able to more so focus on the bevel tips themselves.
2% laminated?
Yeah, that's what will be welding in the video, is 2% laminated.
So if you're gonna run the hot pass fill and cap, would you still use 2% lanthanated, or would you switch to pure?
Essentially, because I do not need the penetration characteristics of what I would get away on the root pass, I'll switch over to a pure, yes, a green pure. And the reason being is because with the ball here, it has a wide cleaning action. It's a bigger surface tension, yeah, and a shallower penetration, so I'll be able to clean more and really get in there.
Makes sense, makes sense. So, routine. What is the routine for aluminum? First things first.
Well, essentially, when it comes to different metals, you have to think in, it's almost like neurolinguistics programming, where you find similarities in different aspects of metal, even though this is aluminum welding we'll be doing. You also have to think about, in relation to nickel alloys, chrome, is that basically you're always heating up, and there's always a routine that you have to follow in order to be successful in this particular metal. This metal right here, what I'll be doing is I'll be heating it up, but I'll be heating it up to 250 Fahrenheit for the root pass. Heating it up helps the weld puddle wash out a lot better. It helps it clean, etching, remove oxides a lot better. It helps the weld puddle break down the parent material or the previous pass. And also it allows for travel distance, so that I'm not traveling so slowly with the weld puddle trying to break down the parent material where it starts to form oxides.
Okay, okay.
Are you gonna keep it under a certain temperature?
Keep it under 600 to 700.
Okay.
Yeah.
I'm gonna keep it under that. Okay. So it's recommended crucially for you, your personal preference, to preheat these aluminum pipes?
Within reason. It depends on the thickness, it depends on the application, but something this thick, and I do know that helium will turn a 200 amp machine into a 300 amp machine and help with penetration characteristics. And but for personal preference, I find that it just helps with breaking down the parent material. And it helps with washing out if it's preheated.
Okay. Okay. Sweet. So brush off oxides, like you said, pure tungsten, for the hot pass, fill and cap, and 2% lanthanated for the root pass. Personal preference for you. What you recommend for everybody else as well?
Within reason.
Within reason.
Because a lot of this is all it's just personal preference, and many welders use different. They may use pure the whole way through. They may use a completely different zirconium or zirconiated tungsten. They may use something completely different. Aluminum is a very wide range. It's a very, very common metal in a lot of places. So they may use different depending on personal preference. Okay,
so now, anybody that's pretty much thinking, can I use a wire wheel for that? Can I use any mechanical tools for that? As far as, a grinder or anything like that to prep it up easier for me. That's what they're probably thinking. If anybody hasn't welded aluminum before, probably go, well, I could just probably wire wheel it or something. What would you tell them?
When it comes to aluminum welding, this is one of the very first things. This is one of the reasons why I spend a lot of time at a place called GRB College of Welding, and I take a lot of Jerry's courses there. Is that when I was learning how to weld, and Jerry at GRB has always seen me from the very beginning, learning how to weld 60-10 roots, 718 fill and caps, to learning all the various different metals, carbon, chrome, nickel alloys, pipeline, etc. But the one thing to understand is that every individual metal, you almost have to think of yourself as a psychologist, and every metal has its own personality, personal quirk, and you have to interact with the metal, and you have to treat it very differently. But when it comes to tooling and applications, you got to use cold means, anything that will not create friction. Friction creates heat. The atmosphere now starts oxidizing material, and it starts to embed oxides into the material. So essentially, you'll be using woodworking tools. This was actually something that when I was at GRB, Jerry had given me a wood router, a stainless steel hand brush. There was no emery cloth, because on other materials you would use emery cloth to clean the filler metal. You would use emery cloth on the material internally and externally, but aluminum, because it's very soft, emery cloth sandpaper embeds the particles into the material here, and they'll start to come out while you're welding. So you have to be very conscientious of what materials you're using, including grinding discs that are made for aluminum. Those still create a lot of friction, create a lot of heat, and create a lot of oxides. So if you're doing pipe welding, do not use grind discs that are made for aluminum. Use woodworking tools, wood router, and also when I was first learning how to do this in the course there, I had to do my own prep work, and Jerry gave me a wood router, and he gave me a wood router bit with a tiny little wheel in there, and you'd have the wood router, and you'd place it on here, and the wheel would kind of ride around the pipe, and basically like you have aluminum flakes flying everywhere. It's like woodworking. It's like just woodworking all over. It basically the welding booth looked like a snow globe, essentially. Wow. Yeah, it's all over the place. I even said to Jerry, it's like a snow globe in here.
It's insane, brother.
But when it comes to this material, generally woodworking tools, you'll not use a bit carbide. Yeah, you'll not use a carbide bit because of speed and everything. It gums up the bit. Okay. Even a file you'll find will be gummed up. And also on the stainless steel brush, a lot of the oxides will go onto the stainless steel brush. But you'll be using woodworking tools, wood router, wood chisels, and wood routers, bits, etc.
Okay, sweet. So now, when it comes to aluminum, the settings in the machine, you're running AC or DC. Let these people know, especially because, like I said, it's an introduction to aluminum. Even though we're doing an open root pipe, the machine, we're using a Miller Dynasty 350. Yep. What's a recommended machine for aluminum?
Essentially, as long as you have a machine that is AC capable, which has the negative for the welding characteristics and the positive for the cleaning action. Essentially doesn't matter relatively what machine, you can still do the welding as long as it's AC to do the welding. Different hertz, I'll be running probably about 120 to 160 for the frequency. I'll be hertz maybe about 65, which is the balance of the positive and the negative. On the Miller Dynasty 350, we can independently change the electrode or the positive side and the negative side, which is the cleaning action and the welding action. We can also change different waveforms in the secret menu. You just hit the average button and the dig button, and you can change through all the settings and change the waveforms. I believe there's a sine wave, triangular wave, advanced square wave, and soft square wave.
Oh, okay.
Oh, sorry. But also welding, there's many applications, there's many different things that are be welded, many different thicknesses, many different alloys, and many different filler metals, and also personal preference. Also, depending on the application, many welders may use, if they're using welding like a corner joint or a butt weld or something, or a manifold, their adjustments and variables on the machine will be wide range. They'll try different frequencies, different balances. They'll change the positive side and the negative side independently. They'll change the square wave, or sorry, the different waveforms. So there's many variables to it.
Okay. Abraham, you had a question for him?
What wave would you be using?
Pardon?
What wave? Square wave, triangle wave?
Right now I just have it on advanced.
Okay.
Yeah.
Okay.
Yeah.
So foot pedal. You recommend foot pedal?
Foot pedal does help because right now we have high frequency and arc. Essentially, because aluminum melts at a very, I believe the melting temperature is like 660 years. It's something really, really low. But really quick. Yeah, but you want to initiate an arc without touching the material here. And also, when you break the arc, you want to protect the tungsten itself away from the atmosphere, because what happens is when the tungsten oxidizes, it'll turn blue and everything. Yeah. Usually, and because aluminum is at high temperatures quite often, depending on how hot the material is, depending on the thickness of the material that you're welding, it may be at high temperatures, and when you break the arc, you want to hold the tungsten over the material because you're protecting the tungsten. And usually when it goes silver, you can count for another 8 seconds and you can turn the gas off. But if you turn the gas off when it turns silver, then it'll go light straw color, because the temperature the tungsten's at is going to interact with the atmosphere and go light straw or yellow. But if the tungsten's blue or purple, whatever, it's very easy, very brittle, so you can easily break it off, where when it turns silver and is protected away from the atmosphere, it's very difficult to break.
Okay, sweet.
Yeah, so essentially when it comes to the routine, because this metal, one of the things that a welder finds when it comes to different individual metals is that different metals have a certain routine. Like for example, when you're welding titanium, you'll do the welding, and then you allow the material to cool, whether it's cooled by air or allow it to cool in the presence of the atmosphere. And then you'll form the cleaning, or sorry, you'll form the prep work, and then you'll perform the cleaning and then the welding. But when it comes to the routine for aluminum, because I'm going to be heating this material up, I'm going to clean I'm first going to clean the filament metal, because the filament metal is exposed to the atmosphere and it's not heated up or nothing, so it's not going to rapidly form oxides at the moment. But basically, I'm going to take the filament metal, and I'm going to clean the filament metal with gas and antifreeze. I could use gas and antifreeze, acetone. The filament metal is going to be clean first. And then what I'm going to do is I'm going to heat up the pipe. Now, when I heat up the pipe, the problem with aluminum is that the hotter I get it to, it starts rapidly forming oxides very, very, very fast. So it's going to, when I heat it up to help try and weld it, it's going to rapidly form oxides. And that's one of the biggest problems with aluminum, is the rapid formation of oxides to protect the material. But it's going to form oxides rapidly. And immediately I'm going to brush the oxides off in the weld zone and the heat effect zone. I'm going to brush those oxides off in one direction, and I'm going to attempt the weld. But that's after it's been heated up. And the other thing with aluminum is that it takes the heat. You could heat up something to, say, 400 degrees Fahrenheit, and you can start welding on it. You get a full length of welding electrode in there, and you can check it with the temple stick, and the heat's gone already. It's already under 400 degrees Fahrenheit. It pulls the heat away depending on the thickness of the material. But yeah, and then after it's welded, you'll protect the tungsten away from the atmosphere, and then you can either allow it to cool. Well, actually, sorry, no. You'll protect the tungsten, and then you'll prep with woodworking tools. You'll prep the material, and then you'll clean the filler metal and then heat it up again. Yeah. So it's certain steps.
It's a little time consuming, isn't it?
Oh yeah.
Yeah, it's time consuming, but it's worth it because you want to make sure you're doing it the right way.
Yeah.
The right way. All right, Travis, we covered that, the routine. Now, what is this down here on the board that you have?
Basically down here, this is certain things to keep in mind while you're welding. This is just for the root pass. But the reason why I'm putting out so many different numbers is because when you reflect back to, say, neurolinguistics program, when you read those books, they're not particularly welding books, but they're teaching a person how to learn and how to be more observant. And in the book, it talks about the modes of learning. So you'd have unconscious incompetence. So if you're a welding student and you basically you'd be incompetent to doing something, but it'd be unconscious. So you would be incompetent and you wouldn't know that you don't know how to do something. Then you would have conscious incompetence, which would be you would know that you don't know how to do something. And then you have conscious competence, which that you have an idea how to do something and you're relatively competent at it. And then your unconscious competence, which that you could do something second nature. Also in neurolinguistics, it talks about that the conscious mind is able to do it's able to control and think of 7 plus 2 minus 2 different things at a time. So how this comes into play right here is that when you're doing the root pass, these are the things I'm having to think about. And basically a person who's even conscious and competent is still going to mess a lot of these things up. And relatively, when you weld aluminum, you have to be conscious competence or unconscious competence, but you still have to think about it. Basically, the first thing first is that you're going to hold the torch perpendicular. And the reason why you hold the torch perpendicular, and this is something that Jerry at GRB College of Welding has always explained to me, and about the importance of welding and the creation of oxides. Basically, if this is my weld puddle right here, okay, that's my weld puddle right there. If I hold the torch perpendicular, the ID of my SIG torch, for example, is going to protect not only the weld puddle, but also the heat affected zone of that particular weld puddle. So it's not going to start forming oxides ahead of the arc. It's just going to, I'm going to form a weld puddle, and everything is going to be protected of that weld puddle. And that's how you can get away with welding titanium, creating a weld puddle and holding the torch perpendicular, and you can protect each individual ripple, and you can deposit metal with protect all deposit metal away from the atmosphere without having to use a trailing shield. But when it comes to aluminum, you want to hold everything perpendicular because you do not want to form any oxides ahead of the arc. And when you start adding an inclination, say 5 degrees, 10 degrees, or even walking the cup or something, and a lot of times when guys are moving from different metals, carbon steel, etc., a lot of times they start out of habit. They start holding the torch at a little bit of an angle, and the weld puddle ends up going from round to slightly oblong, and the torch is down here. And what you're actually doing is not only you're protecting the puddle down here, but you're also heating up the leading edge because the weld puddle is going oblong. You're heating up ahead of the arc, and it's starting to form oxide. So when you have an oblong weld puddle and you start you have the formation and creation of oxides, and you start welding over those oxides, and those oxides, because they melt at 300 degrees Fahrenheit and they melt at higher temperature than the base material, they end up as porosity in your weld zone. So now when it comes to perpendicular, essentially what I'm talking about is if you have a 90-degree carpenter square, perpendicular is straight up and down. So if this is my pipe, it's straight up and down. So any deposit, the weld ripple weld puddle here is going to protect away from the atmosphere. And when I'm talking about adding an angle, it's holding even a 5 degree, 10 degree angle, and you're making the weld puddle go oblong, and all the arc, the metal ahead of the arc is going to start oxidizing. So when you're welding up to that, you're going to be welding over oxide.
Okay. Makes sense.
So that takes care of the whole torch perpendicular. Now the next thing is the maintain 1/16 keel, and this is actually something that when I was at GRB College of Welding before I came here, I was there on the 27th and 28th practicing with titanium and aluminum, and I always go to Jerry just to make sure that I'm good enough to do these metals all the time, because I always look to him to help me with getting to better myself. But in our conversation, he was mentioned to me about the 16th, always maintain about penetration. So if this is my bevel here, you want to have at least a form of 1/16 that is chewing away into the parent material or previous deposit pass. It's going to be chewing it away. So essentially, every time I open a keyhole, because that's what I'm going to be doing on here, is I'm going to be opening a keyhole. My torch is going to be on the leading edge. I'm going to be opening a keyhole, and I have to maintain that it melts one bevel tip 1/16, at least 1/16, and it melts the bottom or the side bevel tip 1/16, and then I can dab into it. Unfortunately, if I do not do that, if it's less than a 16th, then there's a chance that when I dab into the fill metal, the root pass might not even go in there. The other thing here is dabbing into the middle of the hottest points in the puddle. So when I create the weld puddle, I'll see it very glossy, shiny and clear, and I have to dab into the hottest point, but I also have to be very conscientious of the influence of gravity. Depending on whether it's a 2G, a 5G, or a 6G, gravity influences the pipe very differently. So depending on the position of the pipe, I have to dab either, if it's say for example, if it's a 2G, I have to always add fill metal to the uppermost portion of the pipe, and gravity pulls it down.
Exactly.
And even on a fill pass, otherwise it ends up as a bell shape. So if this is my weld here, and I have to add fill metal at the top, and it'll come out, gravity will pull it down uniform. Otherwise, if I add fill metal to the bottom, it comes out like a bell.
Yes, exactly.
So that takes care of dabbing into the middle of the hottest point. And these are things the person has to be consciously aware and thinking about. And these are things that the conscious mind can do 7, 2 plus 2 minus 2 things at a time. Keep the tip of the fill metal within the shielding gas envelope. So also on aluminum and titanium and other metals, and that's why a lot of welders, they have a lot of difficulty with these particular metals, is because you have to avoid the formation of oxides in general, especially titanium. You have to avoid the formation of oxides, and basically you have to keep the tip of the fill metal always enclosed within the shielding gas and of the torch. And when it comes to adding fill metal, you're going to be doing an up and downward motion. So you're on the leading edge or in the middle of the puddle, but it's always an up and down motion. And that way you're always protected within the shielding gas, within the ceramic cup, the atmosphere of the ceramic cup. Some guys, you can watch them, they may pull away rather than up and down. It's pull away, so they're removing the tip of the fill metal away from the shielding gas there of the ceramic cup. So it oxidizes the tip of the fill metal, and then you're reintroducing oxides into the parent material, or into your weld puddle, and you're going to get oxides. Take care of that. The other thing with aluminum is that you have to be. Aluminum is the unfortunate metal that you cannot touch with your tungsten, because you can get away with, say, if you're welding stainless steel or something, or carbon, chrome, you can accidentally touch the tungsten. It's not a huge deal as long as it doesn't get a tungsten inclusion, but you can touch it, oops, okay, and then you can keep on welding. But on aluminum, unfortunately, if you even touch the tungsten, sometimes if your tungsten gets very close, you'll kind of hear the machine buzz a little bit differently.
Yeah.
But the second it touches, it makes like a huge little micro explosion, and you get black soot everywhere, and it just contaminates the tungsten, contaminates the weld zone, and it embeds. You can embed tungsten into the material. It contaminates the aluminum contaminates the tungsten as well. So everything is basically contaminated. That metal has to be removed with woodworking tools, a wood router, or a file, because when you file it, you will find embed tungsten into the aluminum material.
Wow. So you gotta be super cautious.
Oh, it's terrible.
Super cautious. Okay.
Yeah, it's terrible.
Yeah, I see that.
But that's why these are things that a person has to consciously be aware of, and that's when it comes to conscious competence or unconscious competence. Is that hopefully when you get to a point where you do something subconsciously or second nature, that you don't have to think of this stuff. You can think about other stuff like what you're going to do after.
Yeah.
You know, but these are things that a person has to be consciously aware of. That's protected the tungsten away from the atmosphere that's already been covered. Stab up and down has been covered, and then with gravity it's been covered. But also when it comes to these metals, usually when it comes to all forms of welding, you can be invested into something for about a week, say, or a month. You're on a job for a long duration. A lot of these things become you could end up where a lot of the things you do are second nature. And then say you take a month off or 2 weeks off, a lot of the things that you're doing, you become complacent. And then you take a month off or some time off, and then you come back to the metal, and it's almost like you're relearning how to do it. But because originally when you became complacent, now you're more consciously aware of what to look for, and you're paying more observant, and you actually end up learning, and you end up observing new things that you have not seen previously. So when it comes to practicing, it's almost, rather than keep practicing the same thing over and over and over again, hoping that you get it, it's better if you practice something and then you take time off and then you come back to it, because you will be more aware and more observant, and you'll learn new things that way, taking time off, than you would if you were consciously practicing something.
Interesting. I did not know that, but now Travis.
Neurolinguistics.
Neurolinguistics. So me, my personal thing was, to practice, every day to become second nature, because muscle memory for you. But that totally makes sense, because there is times that when I am welding and I take a week off and I come back, I learn something different. I learn something. I'm more focused than I was when I was a week ago, and I see these things. I see more clear the puddle and everything. I'm like, that's different. I haven't seen that the last time. So that's really that's something that shocked me right now. I learned something right there. So that's crazy. That's crazy. Anything else, Travis?
Yeah. So essentially, the things that we're doing in this welding video, they're just a demonstration. They're just a demonstration to give the viewer an idea, almost like an introductory of different materials that you're welding, titanium and aluminum. They're also this video allows the viewer that this welding may be something that may interest them, and because a lot of the information, this is just ideas that are given to the viewer. They themselves, they may find this particular welding interesting, and they may look for a welder testing and training facility to learn how to do these things. So this is essentially, in this video, is just a demonstration. So essentially we have South Coast Welding Academy that will be doing the aluminum welding in the course here. Yeah, so if you're in the States or around the States here, there's South Coast Welding Academy. The place that I've gone to, that I've been going there since November 2008, is GRB College of Welding in Edmonton, Alberta, Canada. And I always talk with Jerry, especially the life and death questions, the most critical questions. I always go and see Jerry. And the other thing is, when it comes to practice, the way I always think about it is that you learn something, you do a welding course and you learn something, but I personally buy the material, I buy the pipe, I buy the machines, I buy all the tools, and I start practicing a lot of these things at home. And then I get to a point where I have a lot of unanswered questions, and there's a lot of things I need to know that I don't know and I don't understand. So I go back, I formulate what questions I need to ask, and I go back to GRB College of Welding, and I ask Jerry these specific questions. They're more detailed, more critical questions. He gives me these new answers, these new techniques, these new ideas, and I go home, back again, and then essentially I level up again. But it all comes with practicing, first taking a course, learning how to do the introductory of aluminum or titanium, and then practicing on my own, coming up with questions that I need to ask, things I need to know, going back to the training facility. In my case, it's Jerry at GRB College of Welding. Once I take what he gives me, I go back home again, and essentially you always level up. So you always need to find somebody that knows these materials inside and out. And I've asked very, very difficult questions, very intricate questions that I've never been able to stump him, and I don't mean that I don't mean to do that intentionally. It's just that the questions I ask are extremely particular and very in-depth, and he's always been able to give me an answer, and he's always been able to demonstrate it on a drawing board, show me in person, show me through books. He's always had an answer for everything. So I've always been very fortunate to have Jerry at GRB College of Welding to always show me how to do these things and always get me to the next level.
Nice, 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 nice. So it's always good to give back, regardless of how many years of experience you have in welding, whatever the case may be. This is what we're here for, is to give back. And Travis here, we're coming all the way from Alberta, Canada, to come here and teach this to us, aluminum and titanium, because me and Abraham, you know, we're not perfect by no means. We're still learning every single day, and I want everybody to know that. Even Travis himself, you know, he's still learning every single day. When I look at him, I'm like, this guy knows it all already, right? But he's still learning every single day. He still has questions. We're all human. So this is awesome. Travis, I appreciate you. So is there anything else that you need to tell the viewers, or you want to just go straight to it and just go out, fit up and just start going?
Well, when it comes to these different metals, like I was saying before, you have to consider yourself as a psychologist. You're dealing with all these different metals, or all your crazy patients.
Yeah.
They all have these quirks and personalities, and you have to interact with them and figure out how to deal with them. Like titanium is nice that you have the troubleshooting. The titanium is very cause and effect, and it kind of gives you an idea and it tells you what's going on. Aluminum is difficult. Aluminum, there's things that this bottle does that I may follow a certain routine. It's clean and it's washed down and it's antiseptic and everything. And the material still does something that I just don't know why. And
He's like,
there's
nope.
so many variables with these metals.
Yeah.
So many things to consider. And also the purge quality and the formation of oxides from the titanium video in parts per million also equate to aluminum as well, because as you heat up aluminum, it rapidly forms oxides. And with lesser parts per million of oxygen, lesser oxygen in the atmosphere that is on aluminum, lesser thickness of oxides and nanometers that you're going to form. But the other thing with aluminum is that it does not form heat tint like it would for stainless steel, in the sense that, you know, it's not going to have light straw, yellow, blues, purples. It's going to be silver. It's going to be shiny version of titanium, and it's very just do not weld over the shiny silver.
So like I said, like if you don't know what parts per minute, correct?
Parts per million.
Parts per million.
Yeah.
Parts per million. There you go. Parts per million. If you don't know about that, you can go to titanium tutorial, which is our last tutorial, and you can check that out. He goes into strict detail on that. So.
Oh, actually, the last thing.
Yes.
Also, when it comes to aluminum, it's a very difficult weld. I've gone into GRB and I've booked my own weld test to make sure that I could still do it, and I've had it where I've done everything I could and I've still broken the my bend coupons like a twig. Because the oxide melts at 3700 degrees Fahrenheit, and because the material underneath the oxide melts at 1220, and these are numbers, you get different numbers in different publications. Essentially, you have to be very conscious and careful. Do not weld over the oxide, because the weld puddle is not going to melt the oxide. It's not going to remove the oxide. And basically what happens, and I'll give it a little example here. A couple years ago, I was on a job site and I was welding 10-inch aluminum piping. And the foreman, this is something that Jerry had always explained to me, is that if you are the welder, you are the expert. And a lot of these companies, they see aluminum as shiny and lightweight. That's all they know. So while I was doing this welding, it was taking me a little while to do the welding, because there's certain steps I have to do in order to successfully weld this material. The foreman was very frustrated with me because I was taking a long time and I was doing everything in steps and everything. I was very particular, and he wanted this material gummed together because this particular application was not going to be X-rayed. It was just going to have plastic pellets flowing through it. But the problem with that, and I explained it to him, but it kind of went over his head, is that I explained to him that the oxide melts at 3700 degrees Fahrenheit. The material underneath the oxide melts at 1220, and because my weld puddle does not remove the oxides, I cannot just gum it together. I cannot weld over the oxides. I just cannot just keep welding, because the weld puddle does not burn out the oxides. The oxides just fuse and mix in with the weld puddle, and they'll always be there. And in the application where it's vibrating, and even if you go through a nick break test, eventually it's just going to crack because there's no integrity in the weld puddle. Because the oxides, and this is the thing that separates aluminum separates from other metals, is that the oxides melt at such a high temperature they always have to be removed.
Okay. Wow. So it went over his head, huh?
Oh yeah.
Hey, but you know, sometimes you just gotta do it the right way. It's always good to do it the right way. Don't try to skip it. You know, like Travis said, the welder knows. We're the experts at this, and sometimes the people that are higher or whatever the case may be don't really know. They just look at the metal and see that it can be welded together and just keep going production-wise.
But they also, because they're not familiar with the different metals,
exactly,
they automatically assume that every individual metal welds identical to one another.
Mm-hmm. Yeah. Okay. Yeah. So, alrighty, Travis. Anything else?
Nope.
That's it. Alrighty. Alrighty. So, guys, we're gonna go ahead and tack it up. It's gonna be in the 6G position, and Travis is gonna take it from there. I appreciate y'all. Peace.
Okay, so basically when it comes to feeding, you have to be very precise when you open the keyhole, when you add filament metal to the material here. So I'm going to hold the TIG torch perpendicular, but I'm going to have a pad because this material is going to be at 250 degrees Fahrenheit when I do the root pass, and I'm going to heat it up to about 400 degrees Fahrenheit when I do the rest of the passes. It just helps with the flow and the puddle and break down the material that I'm welding on and remove all the oxides. But essentially I can feed it. You have to consider how a person feeds, so there's different ways you could just kind of roll it a little bit. You could feed it like this, so I'll hold it like that. You could feed it that way, you could feed it that way, you could feed it that way. You could just roll the fingers a little bit and feed it that way. You could hold it like a syringe and feed it that way. But essentially on this aluminum, just what's going to happen is I'm going to have my hands at a V formation, so it's like a V. The torch my fingers are going to be resting against the pipe, and the TIG torch, as I progress around the pipe, will always be perpendicular to the pipe. When I add the filament metal to the pipe, I'll have my fingers, the torch or the filament metal between these two fingers, and my thumb will always be moving the filament metal, and I'm holding it this particular way just so it stabilizes the filament metal when I add it. When I open the keyhole, I have all the time in the world to add filament metal. So if the pipe wants me to add filament metal and it's hot and it wants me to go faster, I don't have to. I just hold the keyhole and I can add any time I want, so I can adjust the arc and everything until I'm ready to add filament metal. So essentially that's just how I'm going to do it, and when I progress around the pipe, I'm going to be sliding on this heat pad here so I don't scald my fingers here.
Now, I have a question or something to say. For people I know sometimes it's hard for people to keep that the torch perpendicular. A good indication is you got to pay attention to your keyhole, right?
Oh yeah.
If you have a nice circular keyhole, that means you're holding the torch perpendicular. If your keyhole starts getting oval shape, that's an indication you got to fix your torch position.
Yeah, but also that if you're holding the torch, at an angle, say it's not perpendicular, but say you're holding at an angle, when you start adding the filament metal close to the weld puddle, your tip of the filament metal is going to ball up, it's going to oxidize very badly, and it's going to droop down.
Okay.
Yeah, this is very oxidized, very rough metal.
There's two things you can watch out for to see if you're actually holding that torch perpendicular.
Yeah, but essentially the biggest thing here is that for when welding aluminum, when you open the keyhole, you have all the time in the world you want to add the filament metal, and you have to be conscientious of how you add the filament metal, because you can't dab it at the side. Mm-hmm. Right now I'm coming at the side, you have to be more at an angle and dab it more at a stream angle and dab. And then when you dab it, it's not dab and pull away, it's dab and lift upward, so that it's always protected away from, protected within the inert gas. Because if it's dab like this, it's good. If it's dab like this, then it removes it away from the atmosphere.
Nice, man. Nice. Interesting.
Yeah,
Very
that's
interesting.
going to help out a lot of people.
Help out a lot.
Yeah.
Nice, Travis.
All right, now this is another thing that Jerry at GRB College of Welding had taught me, was welding stainless, nickel alloys, duplex, super duplex, titanium, aluminum, particularly aluminum, is that I have the tape right here. The tape is going to go on like this. What I have here is I have 3 layers of one side of the tape, and then I have 2 layers of the back side, so the tape has been reversed and stuck to the back side. So essentially the non-sticky side of the tape is going to go against the weld zone. And basically the reason why that is because when I heat up the tape, I do not want any of this tape residue in my weld zone, and also heat effector zone, and even anywhere relatively close to the weld zone. And the reason being is because if there's any tape residue, when I start brushing the weld zone and heat effector zone, I do not want to remove oxides. I do not want tape residue brought into my weld zone, especially if tape residue contaminates my hand brush, which ends up into my weld zone. Typically, you clean the material with gas and antifreeze, you'll clean the fill metal, you clean the pipe and everything with gas and antifreeze. But when it comes to tape residue, I found that the easiest way to remove tape residue and most efficient way seems to be rubbing alcohol, even though it is flammable. Rubbing alcohol does remove tape residue away from the heat effect zone, and that is part of prepping the area for welding. Okay, so essentially we just preheated the pipe up to 250 degrees Fahrenheit, and the reason why I went with 250 Fahrenheit because it's hot, but it's not going to scald my hands or nothing. So essentially I'm brushing the oxides off, and the oxides do remove a lot easier when the material is hot, but it's still, even though at this temperature it's rapidly forming the oxides really quickly. Essentially, if you look at the pipe here, you'll be able to tell exactly where I brushed, mostly down here. Oxides are coming off now. Same with over here. Now, even though this is taped, I'm going to put a piece of tape right here because there's a good chance that my hand might come up and peel this back. Some I don't want, so I'm going to put this tape on there. Now when my hand slides on, it's not going to interact with the tape and peel it back. So essentially what I'm doing here is I'm just removing the attack with the file, and as you can see, even with slow movement, it does contaminate the file. And going in this direction, it also has aluminum particles that fall into the pipe, which not necessarily you really don't want. But once the tack is gone, and you want a new file. So once that's gone, I can pry the tack out, and then there's all oxides underneath the tack, so those I gotta clean. And then once those are clean, then I start working on all the starts and stops. So I have a nice start there. That was done with the file, just going in this direction. It's all done with the file, and then the tie-in at the end here, that will need to be filed. So I'll file that and have a nice, really nice ramp.